Hello and welcome everyone to our Fronius webinar. Today we shall be discussing the topic obtaining the best solar yield with Fronius inverters. So basically we shall be discussing how, as an installer or a design engineer, how you can derive and of course design a system that will yield the best solar yield, of course, using Fronius inverters. So to do this with me today are my colleagues. First off, Byron Kutzer, who is the technical sales advisor for the Southern Africa region. He's based in Johannesburg, South Africa. And then David Mwangi, he's based in Nairobi, Kenya. He is the technical sales advisor for the Eastern Africa region. And then, of course, myself, Cyprian Okolo, based in Lagos, Nigeria. I am the technical sales advisor for the Western Africa region. So together we shall be making this presentation, and I hope you all enjoy the content we have for you today. So just to note that Byron will be on our chat support. So if you have any questions, please do send them across, and then he will do his best to answer all your questions as they come. So the agenda for today is, as you can see, we'll be going through PV panel optimization, maximum power point tracking, the dynamic peak manager, and then of course active cooling, otherwise known as the thermal dissipation method employed by Fronius. So all these are packaged or intended towards getting the best yield from your solar system. So without further ado, let's now continue to the main presentation. So first off, let's now discuss the factors that affect solar yield. So what are the factors that affect solar yield? First off, we have geographic location, time of the day, period of the year, atmospheric conditions, PV panel layout, PV panel orientation, temperature, and then of course, DC cabling. There could be other factors, but then these are the main ones that I've pointed out. But then even as we have pointed out these 8 main factors, the first four here are basically natural factors. And then the other 4 are factors that can be, improved upon or worked on in order to increase or derive the best yield from solar panels. So we shall, in this presentation, we shall be focusing on these 4 factors, starting of course with the PV panel layout. So let's take a look at PV panel layout, of course, looking at both series and the parallel orientations. So for a series layout, the best practice is that all modules in series should be of the same type of module from the same manufacturer. That is the recommendation. So it is advised that we should never mix panels with different short circuit currents in series. So for more flexibility, you can of course mix panels with different open circuit voltages in series. Excuse me. Okay, so in order to buttress this fact, or for us to see the effect of these notations that have been made, let's now look at what happens. And before we do that, we should note that the performance of the solar array is as strong as the performance of the weakest element. So let's now go ahead with some illustrations to prove what we have said earlier. So let's take a look at this series circuit. So we have 3 panels in series, all with power specifications of 400 watts, with their respective open circuit and short circuit, and open circuit voltage and short circuit current values, which are 40 volts and 10 amps respectively. So to calculate the total voltage of this orientation, it is 40 plus 40 plus 40. That gives us 120, because voltages in series basically the summation of all the respective voltages. And then for the current, it's equal to, because the same current that passes through the first panel also passes through the others. So the total current is just the same as the current that passes through all the voltages, which is the same as 10 amps. So the total power is equals to the total voltage multiplied by the total current. That gives us 120 by 10, and then I have a value of 1,200 watts, which is basically 3 times 400 watts. So this design is good. How about another scenario? So in this case, we have 2 panels of the same specification, 400 watts in terms of power, and then open circuit voltage and short circuit current of 40 volts and 10 amps respectively. But for this particular panel here, we have 200 watts and an open circuit voltage of 20 volts, and but the same short circuit current as the others. The total voltage in this case is going to be 20 plus 40 plus 40. That gives us 100 volts. Total current is going to be, of course, 10 amps, as indicated earlier. And then the total power is now going to be 100 times 10, which gives us 1,000 watts. Basically, 200 watts plus the summation of the wattage of the other panels. So basically, summation of all the wattages. So this design is also good. Now, how about a third scenario? In this case, we have the same specification as the latter, as the former. But then in this case, we have a short circuit current of 5 amps, different from the 10 amps we have in the other panels. So in this case, the total voltage is going to be 40 plus 40 plus 40, that is 120. And then the total current is going to be 5 amps. So it's 5 amps because this automatically becomes, the current flowing through this panel becomes the summation of the current that will flow through the entire circuit. So this automatically makes the total current 5 amps. So the total power is now going to be 120 volts times 5, and that gives us 600 watts. So comparing it with what we had previously, we can see that we had 1,000 watts, and then we have a degradation of about 40%. So this is the effect of current on the circuit, on the series circuit. So this design is obviously not an optimal one. So in summary, the total current is determined by the panel with the lowest current rating when in series, as you can see. Okay, so going forward, let's now look at the parallel layout. So for the best practice for parallel circuit is that all modules in parallel should be of the same type of module from the same manufacturer. So it is advised that we should never mix panels with different open circuit voltages in parallel, of course. So for flexibility, we can, of course, mix panels with different currents in parallel. Also note here that the performance of the solar array is as strong as the performance of the weakest element in that particular circuit or string. So to buttress this fact, we have illustrations. So first off, we have the case where we have a parallel circuit of 40 volts, 10 amps, and 400 watts, as you can see in this case. So the total voltage for parallel circuits is the same as the voltage drop across the panels. So if the panels are the same, then you would have the same voltage drop across them as its summation voltage. So for the total current, it is now going to be equal to the summation of all the branch currents, that is the current flowing through each of the respective panels in parallel. So we have 10 plus 10 plus 10. That gives us 30 amps. So when you multiply it to get the total power, we're going to have 1.2 kilowatts or 1,200 watts, which is basically the summation of the respective power of the panels. So this is fine. And then the next is same parallel orientation, but in this case, one of the panel is different, which is a 200 watts panel, while the others remain the same as previous. So in this case, we have a short circuit current of 5 amps in this case. So the total voltage, as mentioned earlier, as you can see, they are all 40 volts. So the summation voltage is 40 volts. Then the total current is now going to be the summation of all the branch currents. That is 5 plus 10 plus 10. That gives us 25 amps. So total power is now going to be 40 volts times 25, which gives us 1000 watts. So which is fine. Next up is a scenario that has 20 volts for this panel, 20 volts open circuit voltage, while the others are 40 volts. And then the current remains the same, that is 10 amps. But then in calculating the total voltage, the summation of the voltage is definitely going to be 20 volts because that is the voltage of the weakest element in this particular circuit. So the total or summation voltage is 20 volts. The total current is, of course, the summation of all the branch currents. As you can see in this case, 10 plus 10 plus 10, that gives us 30. So by the time we multiply it with the total voltage, we will get 600 volts. So with this, we can see that this is not an optimal design because we have mixed it with a voltage lesser open circuit panel with a lesser open circuit voltage. So in summary, the total voltage is determined by with the lowest voltage rating when in parallel. Good. So still talking about PV array design, it's also important to ensure that the number of modules per string that is used meets the optimal value, meaning that it is important to calculate the number of modules that's going to be used in the system so that we don't oversize it beyond its design specification. And good enough, there is a mathematical relation between the number of panels to be used with the respective specifications of both the inverter and the solar module. So as you can see from the formula here, it has to be less than or equal to the division of the VDC max and VOC multiplied by the relation between the temperature and temperature coefficient. So basically, we can have the descriptions of all the notations in the formula are all listed here. So all you need to do is to plug in the respective values. Like I said earlier, all the notations in red can be obtained from the inverter datasheet or technical datasheet. And then all the notations in blue can be obtained from the module datasheet. So once you plug in that value into this equation, you will now get the optimal number of panels to be used for your system design in order to obtain the best module or best yield. So talking about PV panel orientation, the general rule is that PV systems in the Northern Hemisphere should have the panels facing true south. And then the PV systems in the Southern Hemisphere should have their panels facing the true geographic north. So I must make mention here that there is a difference between the geographic north and the magnetic north. So in this case, I am actually referring to the geographic north. Good. So for the Southern Hemisphere, for example, if more energy is used in the mornings, then the panels should be facing northeast. If more energy is used in the afternoons, then the panels should face northwest. Furthermore, the angle that the solar panels should be set at to produce the most energy, which of course is the tilt angle, is determined by the geographical latitude. So it's basically approximately equal to the geographic latitude. So a general rule for optimal solar energy production is basically to set the solar panel tilt angle equal to the geographical latitude. So as an example, let's take Lagos, for example. Lagos's coordinates, this is it, 6.5244 due north and then 3.3792 due east, that is longitude and latitude. So the latitude is actually 6.5 approximately. So hence the ideal tilt angle for panels should be 6.5 degrees facing south. Since it's in the northern hemisphere, then the panels should be facing due south. And for other example, with reference to my colleagues, take Byron, for example, who is based in Johannesburg. So for Johannesburg, the latitude is 33 degrees, so and due south. So that means that panels, the best tilt angle for Johannesburg should be 33 degrees facing north. And then for how about areas like that are very close to the equator or on the equator, which is a place like Nairobi. Nairobi is approximately 1.2. So that gives us the reference of how the tilt angle should be in this particular area. So if you're exactly on the equator, which is 0, then your panels should be flat or perpendicular. Good. So going forward, let's now take a look at the temperature effect. So how does temperature, what effect does temperature have on PV cells? So here is it. When the temperature increases, then the short circuit current of a panel also increases. This, of course, means that it's a proportional relationship. But then conversely, when the temperature increases, the open circuit voltage of a panel decreases, which of course depicts an inversely proportional relationship. So it means that also to note here that is that temperature has a greater effect on voltage than it has on current. To shed more light on this, let's now look at this particular example. So what would be the short circuit current, open circuit voltage, and the maximum power of a 395 panel? So this is actually an example of that we are going to use to buttress the above mentioned. And here we are going to make use of a Canadian solar panel with the respective electrical data and of course temperature characteristics. So in order to answer these questions, of course, we would need the data of the short circuit current, open circuit voltage, and the maximum power at standard temperature conditions. And then would also have to get the temperature coefficients for current, voltage, and power. So we are supposed to calculate the short circuit current, open circuit voltage, and maximum power at this particular temperature, which is 50 degrees Celsius. And mind you, the standard test condition temperature value is 25 degrees. So going forward, this can actually be obtained using the following relation. So all we need here is to impute the values. So here, delta T here stands for the temperature change, which is 50 minus 25. 50, the target temperature that you're calculating for, and then 25 degrees Celsius, the temperature at the standard test condition. So by the time we plug in all these figures, we are going to have a value of 10.96 amps for current, and then 43.71 volts for the voltage, and then 359.45 watts for the maximum power, all to obtain the values at 50 degrees Celsius, as you can see. So by the time you compare it with what we have on for the nominal values, as you can see, so for the current, we had 10.96, and what's given here, the short circuit current at the STC, standard test condition, is 10.82. So there is an increase in current, but then not as much change as we have on the voltage. For the voltage, it was 47 volts, but here we have 43.71. So this automatically proves to us that temperature increase has more effect, a greater effect on the voltage than it has on the current. And same happens also to the wattage. This can also be shown from the temperature coefficients of the power. As you can see, it has more effect, a negative effect, 0.36. Then next up is a negative effect on the voltage, which is at 0.28. Okay, so let's continue. So in this case, it means that in order to reduce the effect of temperature on the panels, please ensure that you tilt your angle to the optimal value as explained in the previous slide. And then secondly, and most importantly, please ensure that you allow a gap between the module and the roof, that is for roof-mounted roof-mounted systems, so that there could be a good degree of air passage under the roof. This will go a long way in mitigating the effect of temperature on the open circuit voltage. Good. Now let's talk about DC cabling and how we can design optimally and by making the right choices of our DC cables. So for DC cabling, the current carrying capacity must be equal to or greater than the current to be carried, meaning that you have to select a cable that should be able to carry the current to the load current. So a good suggestion is always to size it for 1.25 times the nominal current of the system, and also ensure that the cable must be able to withstand environmental conditions. And of course, special attention needs to be paid to the voltage drop, because this also increases with cable length. And then consideration has to be placed on whether the cable is stranded or solid core. Here, I'd love to say here, to note here that stranded cables have more current carrying capacity than single core cables. So please also have that in mind. And then, of course, the specific conductance of the cable also has to be considered. For this example, copper and aluminium have been compared. And as you can see, each of them have their respective conductance. And we can see that copper has higher conductance than aluminium. So, and then, of course, these all contributes to the power loss. Power loss can be calculated by this particular relation, which is I squared R. R, the resistance, can be calculated as given by the inverse of the conductance multiplied by the division of the length. Now the length here, we're referring to the length between the module and the inverter, divided by the cross-sectional area of the cable in question. So going forward, if you plug it into any power loss calculator, this will eventually give you, of course, by imputing also the acceptable loss. Please ensure that the acceptable loss is as minimal as possible, probably 1 or 2%. So if you plug these values in for this particular example, we have a system with a VDC of 1000, amperage of 10 amps, and then length of cable between module and inverter to be 20 meters. So by the time this was calculated, this, of course, gives us the required cable size to be used, which is 1.5 mm squared, which same as 16 AWG. So with this, you can now get the appreciable or optimal cable size to be used for your system. Good. Now, how about maximum power point tracking? Now, before we go into that, let's take a look at a data sheet of 2 inverters manufactured by Fronius. First off, here is the Fronius Echo. Fronius Echo with its respective technical data, of which I'm going to be making reference to eventually. So, but please take note of the short circuit current and then the maximum input current, as you can see. And then, of course, most importantly, the DC input range, which is 580 to 1000 volts, and then the feed-in start voltage, which is the voltage threshold that must be reached for the inverter to kickstart production, and then the nominal input voltage, as you can see. And then also, notably, is the number of DC connection, meaning that we can connect up to 6 strings, and then the maximum PV generator on the DC side. So this means that for the Echo 27, which is a 27 kilowatt inverter, you can actually connect up to 37.8 kilowatts peak solar panel capacity onto it, which gives us an approximate of 140% oversizing value. Good. Having said that, let's look at the SIMO 10 with its respective parameters or technical data. And visibly, you can see that its input voltage range as compared to that of the Echo is, of course, pretty obviously different. As you can see that the voltage window here is quite wide, and I'm going to be talking more about the reason why it is so. So here we have 200 to 1000 volts. Feeding start is 200 volts. Nominal voltage is 600 volts. You can actually connect 6 strings, but then it has 2 MPPTs. That's very, very notable. Here for the Echo, it has 1 MPPT. I forgot to note that earlier. So for the SIMO, it has 2 MPPTs, meaning that you can connect 3 strings to 1 MPPT and then the other 3 to another MPPT. And from the value here, value obtainable here, we can see that it can be oversized up to 150%. Good. So let's now look at the PV production parameters. So in this case, it is worthy of note that to note here that the module current is directly proportional to the irradiation. This means that low irradiation yields low current, and then high irradiation yields high current. So what are we saying? Looking at this illustration, we can see that we have different conditions here, cloudy conditions, partly sunny, and then very sunny conditions. So these all have their respective irradiation values, as you can see, right from 1000 watts per meter squared up to or down to 200 watts per meter squared. And then what you can also see clearly here is that the short circuit current, of course, increases significantly with an increase in irradiation. Also worthy of note, and of course most specifically, is that for each of this point, or for each of this curve, we have what we call the maximum power point. So which is the point where the maximum yield or solar yield can be obtained. So we can see that the MPP of these curves vary from irradiation figures to another. But then most significantly, we can note that the variation in voltage is actually not that much. So we have minimum changes in voltage at different irradiation levels. So what this means is that irradiation has a higher effect on current than it has on voltage. So that's what we're trying to point out here. So what are the main causes of yield losses? Just to summarize, we can have design-related causes, which includes common setup and configuration mistakes, not following recommended procedures, cable sizing, and then of course loose connections. We could also have other effects like irradiation variations, which of course are natural causes that cannot be surmounted. They will have effects of module orientation, shading, which sometimes comes inevitably, and then of course lifetime degradation. So what happens when the input DC voltage is not optimal? So all Fronius snap inverters, except for Echo series, have what we call booster circuits. So this circuit enables inverters to attain optimal production level. So that is what I will be referring to with the data sheet or the technical data that I was talking about in the previous slide, because Echo series actually have narrower operational voltage window. So in order to maintain efficiency, the booster circuit is usually switched on and off depending on the VDC. So for all snap inverters except the Echo series, you have what we call the booster circuit coming into operation. And this kicks in, say, from 300 to about 595 volts. And then once it exceeds this value, the booster goes up. So this, of course, is what we have in the, and this is actually exclusive to Fronius inverters, so as to help them increase their performance, efficiency, and of course, boost their output. Good. Now let's talk about SUPERFLEX design. So what is SUPERFLEX design? In order to explain this, we'd have to take a bit of scenario. from what we have obtainable elsewhere. So some inverters actually have what we call a main and a secondary input. So in these cases, if two MPPTs exist, one takes about 80% of the input while the other takes 20. Other inverters tend to have equal design in terms of their input. So it means that MPPT1 takes 50% while MPPT2 takes 50%. Now it is also noted that none of the MPPTs can take more than 50%. So now this is where Fronius comes in uniquely, because the Fronius SUPERFLEX design combines the two variations stated above, all in one design. High power, it means that even if you have a high power on MPPT A or MPPT B, it's not any issue at all. So it can come in very handy for unsymmetric distribution and shading conditions, meaning that you can have panels oriented at 80 and 20% orientation, meaning that you could have more panels connected to MPPT1, and then about 20% panels of the panels connected to MPPT2. And then, of course, it also can handle symmetric distributions, say for east and west orientations of 75% respectively. So in this case, you can see that it's a system that will sum up to 150% over dimensioning. So what does the SUPERFLEX design address? So it basically addresses, just as we have seen in the previous slide, different orientation of panels and, of course, unsymmetrical PV installation spaces. So as you can see from this illustration, if the total surface area for installation is not symmetric, inverter can, of course, handle unsymmetric and different orientations. So in order to buttress this fact, you can see it from this example, talking about, say, an industrial rooftop, which normally comes with very, very tricky roof orientations. So you have most of them coming in non-symmetric design. So in most cases, also you have them, prompting the fact that all the modules will have to face in one direction. So 2 or 3 orientations are also possible depending on the roof complexity and location. So depending on the orientation of the roof, we can actually have a combination of Fronius inverters that can handle even the most complex of roof orientations. So what I'm talking about is we can have orientation that can be handled by a mixture of simultaneous and echoes. Say, for example, for orientation that is, we have panels that are facing one orientation, we can have them connected to an echo with one MPPT, and then 4 roof orientations like this, for example, which you have 2 orientations, you can have them connected to a SIMO that has 2 MPPTs. Furthermore, we can, of course, make use of the Fronius Tauro 50 kilowatts that has 3 MPPTs. Of course, this comes in with an additional flexibility. So, and then one may ask at this point, how many MPPTs are there ideal for an inverter for an optimal design? This is actually covered in a dedicated topic, a webinar presentation that we already have out there. So please feel free to check them out and then see what you have for you with regards to this particular topic. Good. With that, I've come to my part of the end of my part of the presentation. I will now be handing over to David, who will be continuing with the remaining part of the presentation. So, David, if you're on, please continue from here.
All right. Thank you very much, Cyprian, for the first part of the webinar and for detailing the various topics very well. So I'll now continue to look at what are the specific features inside the Fronius inverters that guarantee that you get maximum or optimal yield from your PV installations. So, and to start, we are going to look at the dynamic peak manager and be able to explain how this works to guarantee you optimal or maximum yield. So the dynamic peak manager is embedded as a standard in all Fronius inverters. So it doesn't matter whether it's the Snap inverters, the Gen 24 or the Taurus. So the dynamic peak manager as an extra MPPT algorithm is already embedded in these inverters. And the way it works is that it locates the MPP at each input voltage, as already shown by my colleague Cyprian. When you have especially an effect of temperature on the PV array, then you get a variance on the input voltage when it comes to the inverter connection. So depending on the input voltage, the dynamic peak manager then works out what is the maximum power point. And this therefore allows faster adoption to changing irradiation levels. And also this would be done like on average every 5 minutes. And after the dynamic peak manager finds a new maximum power point, it compares with the previous power point to check which one is delivering more power to the inverter. So therefore, if you come across situations whereby maybe per design requirements, optimizers were required, you can switch off the dynamic peak manager in the Fronius inverters. And this can be done by accessing the basic menu structure of the inverter. And you are able to switch it off or on at a later stage if you want. But the default setting when you get the Fronius inverter from the factory is that the dynamic peak manager is in the on position. So having said that, we can also now talk about how the dynamic peak manager is going to operate in partial shading conditions. So therefore, how then do you maximize your yield in shaded conditions? So before we get to that, it's good to understand that when you have shading, you're going to have for every PV curve or IV curve, a possibility to have more than one maximum power point. So if you look at this example in this graph, we can see that we have 3 time periods that we are considering. One is midday, which is 12, which you can see in the blue curve. And for this one, we have no shading, and therefore we have the highest possible maximum power point. And then you have another curve shown in red at around 9 in the morning with a bit of shading. And therefore for this one, we have the possibility to have 2 maximum power points. So we can see for the one at 12, we have the global maximum power point, which gives or yields the most power to the inverter. And then when you have shaded conditions, as we can see in the curve for 9 and 8 a.m., we have also a possibility for a local maximum power point. So what the dynamic peak manager therefore in essence is doing is scanning the entire IV curve and being able to distinguish between the local maximum power point and the global maximum power point. And how this is done is by the inverter intelligently varying the operational voltage, which could be done by either reducing the voltage slightly in one direction or increasing the input voltage on the DC side and checking whether the power is increasing or decreasing. When the inverter doesn't have a dynamic peak manager, and therefore it means that once it finds a maximum power point, it starts production at that point without checking the entire IV curve, you can run into some substantial yield losses. So to also show this further, we are going to consider a practical system that is about 3.3 kilowatt peak with a southwest orientation and a tilt angle, which is about 19.5, and which is experiencing partial shading. So as we can see here, there is a bit of a roof protrusion just next to where the modules are installed. And therefore, a bit of shading is expected from around 8:45 in the morning to around 10 a.m. in the morning. As we can see, if the inverter doesn't have the dynamic peak manager, we have a section here on this curve that we are going to lose a bit of power, as shown here shaded in red. So that can be put into perspective when you now bring the dynamic peak manager into the picture. As I already mentioned before, the dynamic peak manager will, even in shaded conditions, partial shading conditions, work out what is the best optimal operating point. And this therefore guarantees that you have more yield and gives you also more flexibility in terms of where you can install your PV array. So as we can see, the green area, as a contrast to the curve before that I had shown you, is what the dynamic peak manager is contributing to the array production when it comes to the inverter output. And therefore, as we can see, because of the dynamic peak manager, you have about 7% more yield of your PV system. And this can also be worked out into actual cost savings or earnings, because if you're going to borrow or get power from the grid to cover the instances where the PV array is shaded, then you are buying power from the grid, and therefore this can be said to be, a cost as far as power is concerned. A quick example here is looking at a 300 kilowatt peak system, which is experiencing irradiation for about 6 hours per day. So 6% of 300 kilowatt peak times 6 would give about 126 kilowatt hours per day. And if the system, theoretically, we say working with about 9.5 months per year, assuming that the rest 2.5 years you have a bit of shading here and there or not very good irradiation levels, then you can have an increase in production or yield of about 35,900 kilowatt hours. And then if you project this further to the entire life of the system, that would mean there's a bit of a mistake here, but this should be kilowatt hours. So this is 718,200 kilowatt hours. If you then consider what is the cost of power, this would mean, for instance, for Kenya, for every kilowatt unit is about 20 cents US dollars. And therefore, if you project over the entire life of the system, this can be a very substantial amount that with the help of the dynamic peak manager, you can have increased or added yields of savings depending on how you want to look at it. Of course, the bigger the system, the more the savings that you can realize by having the dynamic peak manager. All right, so let's now look at something else that is also very, very helpful in Fronius inverters that guarantees you maximum yield, and this is the active cooling technology. So what is the concept of the active cooling technology, and why is it better technology for power electronics? So by definition, so we can say that the aim of the active cooling technology is to proactively provide the creation of hotspots, and this is done by strategically positioning interior fans to remove warm air in a controlled manner. So at Fronius, active cooling is a technology that is standard, just like the dynamic peak manager. So active cooling is standard for all Fronius inverters. So therefore, in addition to a heatsink, there is a fan that ensures that the air inside the inverter is circulated, and therefore no hotspots are created or developed. So further, a fan can be put right inside the electronic boards to ensure that this air maintains a very low temperature. Of course, the speed of the fan will vary, and this is temperature controlled. So if the temperature variance inside the inverter is not very high, then the fan is running at a moderate speed, and then as the temperature increases, also the RPM of the fan are also increasing. So as far as Fronius inverters are concerned, as we can see from the schematic or the illustration to the right, our inverters are taking air from the sides, and especially the snap inverters, and the hot air is escaping at the top of the inverter. So that also conforms to what we know normally, that hot air is denser than, or is lighter than cold air, and therefore moving the air from the top of the inverter is a very good working principle. As far as the Gen 24 is concerned, we have a bit of a slight difference. So you can see that the fan is centrally located, and then you have a huge heatsink on the front of the inverter, and the air is escaping all around the inverter, and therefore also this one achieves very good cooling of the inverter. So active cooling, what is the effect therefore of active cooling on hotspots? So when you have an actively cooled device, so usually two fans, except for the Gen 24, as we have seen, it has only one fan. So one fan is cooling the heatsink, and the other fan is cooling internally inside the electronics. So we can see that we are able to prevent creation of hotspots, as we can see here, and maintain a very good operational temperature for the electronics inside the inverter. On the flip side, when you have passive cooling, we have a device that is designed to be cooled by convection, by expecting that hot air will be pushed out by the heavier air, and then also relying on a bit of air movement or wind to be able to push out the hot air from the inverter. So in most cases, there will be no visible fans, but some passive cooled devices still integrate some fans inside the inverter to basically cool or circulate air inside the inverter. But still, in this case, we are not able to completely avoid the creation of hotspots inside the inverter. So the advantage of active cooling, therefore, would mean that you have less costs in terms of maintenance. So if you have a passively cooled device, you have to be able to account or to put into operation preventive maintenance, especially to clean out the heatsink as dust accumulates over a period of time. With active cooling, you have more yield, so you have better performance, and this guarantees you highest yield from the inverter. You have ease of installation because the inverter has less weight, and therefore, depending on how many people you want to set to the field, for a passively cooled device, you might have to set slightly more people for lifting, because these inverters will come with very heavy or huge heat sinks, which add a significant weight to the inverter. And therefore, when you have an actively cooled device, you can actually avoid a lot of or cut on the cost of installation. With an actively cooled device, it gives you also a lot of flexibility, as you're going to see later. So with the Fronius inverters, you're not limited on where you can install the inverters. And most importantly, an active cooled inverter will have a longer lifespan than a passively cooled device. So, and this is something that is also very, very important also for your customers. Even when we say that probably an actively cooled device might be slightly more expensive than a passively cooled device, but then if you look at the OPEX in terms of what might come through as the cost of replacing the devices, you're going to replace passively cooled devices a lot more than actively cooled devices. So with active cooling, as I had mentioned before, you have more flexibility on where exactly the inverters can be installed. And this therefore allows that with Fronius inverters, we are not that limited. So we can install the inverter from a flat position, that is 0 degrees, up to 90 degrees angle, that is a vertical orientation, without major concerns whether the inverter is going to have sufficient cooling or not. On the flip side, for passively cooled devices, you are sort of limited to mounting the inverters mostly in a 90 degrees vertical orientation only. Also, as I mentioned before, active cooling is going to guarantee a longer lifespan of the inverter. So the hotter electronic parts get, the shorter the lifespan of these parts. And in general, as a rule of thumb, it's been determined that an increase in 10 degrees on the operating temperature of electronics cuts the life of these electronic parts by half. And therefore, active cooling gives less stress on the electronic components, and thereby ensuring a very long lifespan. So overall, so you're going to get more yield with active cooling. So if an inverter is exposed to high temperatures, the most common behavior, if the inverter is not properly or sufficiently cooled, is to derate the power output. So if you have an actively cooled device, even when derating happens, it's going to happen at a much later stage or at a much higher ambient temperature compared to a passively cooled device. So, and of course, derating of the power output of an inverter has a huge impact or a negative impact on the yield. And therefore, if you have an inverter that is actively cooled, as you can see in this graph here, we are able to derate at a much later temperature when you're looking at the ambient temperature conditions. So we are starting to derate at just about 45 degrees Celsius. But in contrast, we can see that a passively cooled device is already starting to decrease the power output once the ambient temperature goes above 30 degrees Celsius. So, and we also have to distinguish between the ambient temperature conditions and the heatsink temperature. Because when the ambient temperature is at 45 degrees Celsius, for instance, we could be looking at a heatsink temperature of about maybe 55 or 60 degrees. So it's important that this distinction is made. So to further give or clarify this point, the effect of derating on the power output of the inverter, we are looking at a 99.84 kilowatt peak system on the DC side, giving out 90 kilowatt on the AC side, and this is an installation in Australia. And active cooling gives more yield, which is about 647 kilowatt hours. But with a passively cooled device, the losses are up to 96 kilowatt hours. So we can see here we have the temperature, the ambient temperature that is tracked from right in the morning up to when the panels or the inverter should be producing the most power at around midday to 1 thereabout. And then as the sun sets, we are also tracking the same temperature. So we can see that with a passively cooled device, as the ambient temperature increases from around 11 up to around maybe 4 thereabout, you have quite a substantial decrease of output from the inverter. But with an actively cooled device like a Fronius inverter, we can see that we are still able to cover the entire production capacity on the PV array side. And therefore, you can see here already that with a passively cooled device, you have significant losses on yield that can be experienced for this particular example. And what has been worked out is actually that if this system is running off a passively cooled device, you can have yield losses of approximately 15%. Also, in terms of maintenance, when it comes to OPEX, active cooling guarantees very minimal maintenance costs. So you will make less trips to site for maintenance. Otherwise, if you are using a passively cooled device, you have to be able to plan for trips at least once every 6 months. And depending on the distances that you have to cover, then these are significant OPEX costs that have to be discussed in advance with your customers. As you can see here, this is just an example from one of the inverter manufacturers that are producing passively cooled devices. And this is their routine maintenance checklist, what has to be checked. So every 6 months, quite a number of things for this particular inverter have to be done. So therefore, when it comes to saving costs, you can say that an actively cooled device is going to be not only to guarantee you more yield, but it's also going to guarantee that you are saving on some of the most common OPEX costs that come up when you're doing PV systems. So, but having said all that, there are of course some myths in the market regarding active cooling and what dangers this poses to the inverter. So we can look at a few myths and claims. So, can devices with a fan achieve IP66? Because this has been a major topic of discussion, and therefore the claim has been that Fronius cannot achieve IP66 if their inverter has a fan. But in reality, the fans are sealed internally and have an rating of 67, IP67, which means that these fans can actually operate even temporarily underwater. And in general also, the way the fans are constructed, they even have a higher IP rating than the entire inverter. So the inverters mostly will attain IP66, but the fans can actually go a step further and achieve IP67. Also, we look at what this means in terms of fan operation hours, depending on the various temperatures. But regardless of the operation hours, we can see that because the fans are controlled depending on the temperature within the inverter, we have still expecting a very long lifespan of the fans, and therefore comparable to the service life of the inverter, the fans are also expected to last for more than 30 years. So these conditions were analyzed for 3 specific regions. So we have Italy, we have United Kingdom, as well as Australia. So, and these are the operational hours per year. And we can see that because, as I mentioned earlier, the speed of the fan is thermally controlled, and it will only run at full speed when the ambient temperature reaches 60 degrees Celsius. And therefore, this means that the heatsink temperature will still be a lot higher than 60 degrees Celsius. So, but in practice, this operating point as shown in this graph occurs for only very few hours per year. And therefore, the fans will remain operating, like I said, comparable to the life of the inverter will be nearly the same. So therefore, that brings us to the end of today's webinar. So for further information, if you'd like more information on the various Fronius products, how to install the Fronius inverters and other products, the Home Pilot and the Watt Pilots, please go to our website, downloads area, and there you are going to get a lot of resources that are useful for that purpose. And then if you want to have a look at the various webinars that we have done in the past, please go to our YouTube channel. There is an African playlist there, Sub-Saharan African playlist. And from that, you can also access a lot of topics that we have covered in the past. For additional support, and if you have any other concerns regarding the various products from Fronius and Solutions, kindly get in touch with the respective contact persons. For Southern Africa, please get in touch with Byron. For Western Africa, get in touch with Cyprian. And for the Eastern African region, please get in touch with myself. But please also, if you want to get in touch with our colleagues in the international or in the head office in Austria, here are the contact details, and you're more than welcome to let us know how we can grow the market together. So with that, we have come to the end of our webinar for today, and I do hope that you have gotten a lot of useful information, and we look forward to welcoming you to our next webinar next week. But for now, goodbye and have a very good day.